Hello everyone. So let's start our discussion for today. But before discussing any further, let's have a quick recap of what we discussed in our previous class. Okay. So we started our discussion with CPU, right? And we also saw that CPU has two basic components, data path and control unit, right? And we started our discussion with data path, right? We saw like how data path looks like. It is basically nothing but a circuitry, right? Then we also saw that circuitry is like a combination of hardware components, right? So then we saw that there are different hardware components of data path, right? There are basic three types of hardware components of data path. What are those? Registers, arithmetic and logic unit, which is ALU, and CPU interconnection, right? CPU interconnection. We also saw that CPU interconnection is nothing but wiring, right? It is nothing but the wiring which is acting as a transmission media between registers and ALU. Registers, ALU, and there is another component here, control unit, right? So control unit, registers, and ALU, okay, and all the hardware components, right? So it is nothing but wiring between the hardware components. Okay, and this is quite important because it is the one that decides the logic, right? It is the one that decides the logic. It is used to implement the logic, right? Wiring decides the logic. Okay, so after this we started discussing about registers, right? We took registers and we started discussing about registers. So we discussed why we need registers, right? Why we need registers, why we need registers, right? Then we looked into hardware aspect of hardware aspect of registers, right? Hardware aspect of registers. Then we looked into a working of registers, right? Working means like the storage aspect, right? How it stores the information, how input comes, and which bit goes to which particular binary cell, right? So we discuss all that. Then we discussed about the types of registers, right? So registers can basically be categorized, and they can be categorized based on two things: the information they store, and task they perform, right? And based on the information they store, they can be classified into two types. First one was data register, and second one was address register, right? Data registers for the registers that stores data, right? Data means instruction and values, whereas address registers for the registers that can store the addresses of cell of memory or IO devices. Okay, and based on the task performed, there were two types of registers. The registers were general purpose registers or GPRs, and special purpose registers or SPR, right? Then we were looking into what are the general SPRs that are present in any CPU, in any like processor, right? So we were looking into the different types of special purpose registers and what are the tasks that they perform. So we saw that there are 9 SPRs that any processor contains. Okay, so let's start our discussion from here. Okay, so these are basic 9 types of special purpose registers. Okay. Memory address register, IO address register, program counter, stack control register, memory buffer register, IO buffer register, instruction register, accumulator register, flag register. So all of these. no need to worry, we will be discussing all of them in great details. Okay. You can see here there is a like a color scheme which I am following here. So you can see that these four are colored green, right? And the name itself is suggesting that these registers generally stores addresses, right? IO address, memory address, program counter we will discuss, stack control we will discuss. So these are address registers. Okay, these are address registers. Whereas the one written in blue are actually data registers. Okay, these are data registers. So they consist either instruction or values. Okay, these are data registers. So before going further, let's discuss a little bit about CPU requests. Okay, so as you all know, CPU CPU is what is a master, right? This is the one which is brain, and CPU which is main memory, right? It accesses main memory, right? And it can do two type of operations on main memory. What are those? It can either write onto main memory, or it can read from main memory, right? It can read from main memory. Okay, so whenever CPU wants to write or read, it it generates a request. It generates a request. Okay, so for a read there is a read request. Okay, and for write there is a write request. Okay, so what exactly is read request? So read request is nothing but CPU sending two things. CPU sends two things to main memory. What are those? CPU sends the address of cell that it wants to read. For example, main memory has cell C1. Okay, C1 is the address of this cell. So if CPU wants to read the content of cell C1, it will send the address C1 to main memory. Okay, so a read request includes the address of cell, and it also includes the signal, read signal. Okay. Read signal. Okay, and these two things will be sent to main memory. Okay, these two things will be sent to main memory. Okay, as a read request. Similarly, when we want to perform any write, V means CPU. Whenever CPU wants to perform any write operation, in that case CPU will send three things. It will send address of cell. For example, CPU wants to write value write value 5. Okay, here in cell C1. Okay, CPU wants to write 5 in cell C1. What it does is it sends the address of cell C1. It sends the address of cell that is here C1. It also tells that this is a write operation. Okay, so it sends write signal, and it also sends the data. It sends the data that is to be written on this memory cell. Okay, so these are the three things that is sent to main memory. Okay, so we generally represent read request something like this. So read request, you can see read request written something like C1 comma RD. This is read. Okay, we generally represent read request like this. Whenever we want to represent write request, we write something like this: C1 write. Okay, C1 is the address, write is the signal, write signal, and the data. Let's suppose 5 is the data, okay, which you want to write. So our write signal, a write request will look something like this, okay. So it basically now this is nothing but sending two things to main memory: the address of cell and the read signal. This is nothing but sending address of cell, write signal, and the data that is to be written, okay. Now let's resume our discussion of special purpose registers, okay? Let's start with memory address register, okay. So what is memory address register? So whenever CPU wants to access main memory, it sends. So we also noticed here that a read request and write request, both these requests contains the address of cell, right? It contains the address of cell. Address of cell is common. So whenever we want to access something, we means CPU. Whenever CPU wants to access something from main memory, what it does is it sends the address to the address of cell. For example, this is the cell. It sends the address of cell. Let's suppose it is 00000001, okay. It sends the address of this particular cell to main memory, okay. And we also discussed that all the addresses are sent via address bus, right? Address bus is used to send the addresses to main memory, okay. And address bus is like connected to CPU through pins, okay. So CPU has pins, and these pins are connected to address bus, okay. So some x number of pins in CPU are dedicated for address bus, okay. And these pins are directly connected to one register called as memory address register, or MAR. We generally say MAR, okay. So this these pins, which are assigned to be connected to address bus, are connected to memory address register, okay. And memory address register is the one that sends any address via this address bus, okay. So whenever CPU generates any kind of request, any kind of access request, okay, any kind of access request, it sends CPU sends the address of cell to memory address register, okay. And memory address register in turn sends this address of cell via address bus to main memory, okay. So whenever CPU has some access request, it will send CPU will send, okay. MAR is the part of CPU, but this is one step. I mean, there is some place where this address will be stored, but that address will then go to add this memory address register, okay, from some register to memory address register. And when it goes to memory address register, this in turn sends this to main memory, okay. So CPU, it can be any register, okay, it can be any register. So this address will pass from any register in CPU to memory address register whenever this access is supposed to happen. Whenever CPU wants to access, it sends this address to memory address register, and memory address register will pass this to main memory, okay. So memory address register here is nothing but an intermediate register that whose task is just to uh, get the address and send the address, get what is send what it gets, okay. I think this is clear. So let's write the definition here, okay. Let's write the definition here. Let me select one pen, okay. So what is memory address register? So memory address register is a register. It is a register that holds address of what? Address of memory, right? Address of memory cell. It it holds address of memory cell whenever CPU wants to access main memory, right? So it holds the address of memory cell where CPU wants to perform a write read or write operation, right? So memory address register is a register that holds address of memory cell where CPU wants to perform read or write operation. Okay, so whenever CPU wants to access main memory, the first thing that it does is it sends the address of the cell to memory address register. Simple. So memory address register is this. Okay, so let's move on to another register. So this is memory buffer register. Okay, let's discuss about memory buffer register. We also call it as memory data register. Okay, we also call it as memory data register. Okay, so what is memory data register? Memory data register is a register that stores data, okay, that stores data that is either read from main memory or it has been written to main memory. Okay, either read from main memory or written to main memory, right? So memory data register is register that stores data that is written from that is read from or written to main memory. Okay, now what does it mean? So we already saw that address bus is connected to like MAR, memory address register, right? Address bus is connected to memory address register. So whenever we receive or we want to send some data, we will do that via data bus, right? So there must be one register that is there to send or receive the data to and from data bus, right? So MBR is that particular register. So what is MBR? So it is a register that holds the content. It is a register that holds the data, and this data can be either it can be either instruction or it can be values, right? So the data part, either instruction or value, will be sent by main memory or received to main memory via MBR. So whenever CPU wants to read something from main memory, this content will flow from main memory to MBR to CPU. Okay. So whenever a CPU wants to read something from main memory, the content or C will go from main memory to data bus to MBR, then to wherever it wants to go. Okay, for example, CPU wants to process the instruction, it fetches the instruction. Okay, now main memory will send the instruction via data bus, and this data bus this MBR will get the instruction. Now the further processing of that instruction will be done by CPU. I mean, it will be done in some way. We will be discussing about that as well, but you can just see here that the flow will be from main memory to MBR to CPU. Like, what is CPU? The other part, the part that is except MBR. Okay, memory buffer register. And whenever CPU wants to write something on main memory, the flow will be content will flow from CPU to MBR. Okay, and then MBR to main memory, right? So whenever a CPU wants to put something on data bus, it will use MBR to do so. Okay, it will send that content to MBR, memory buffer register, and this memory buffer register will put that content to data bus. Okay, so MBR is also directly connected to data pins. We already saw that here, right? MBR is directly connected to the pins, and these pins are data pins, right? So I think everything is clear here. Okay, let me write the definition here as well. Okay, so what is memory buffer register? It is a register. It is a register that holds the content. Now this content can be two things: instruction and value, right? That is to be read. That is read from or written in memory. It is a register that holds the content read from or written to main memory. Okay. I think this is clear. Okay, so now this incoming content, uh, we already discussed, right? It can either be instruction or value, and based on the type of this content, MBR, what it will do is, if MBR, what it will be doing is, when if it gets instruction will be sent to one special purpose register, which is instruction register. Okay, and if it is a value or a data, it will be sent to accumulator. Okay, what is that? It is also special purpose register. We will be discussing about both of them. Okay, and no need to worry, we will be discussing about both of them. So for now I'm just uh, showing you that like MBR is the one. It is kind of like, if this is bus, if this is bus, it is a bus stop. Okay, whenever something is to be sent or received, we will send that information to MBR. Okay, and MBR will put this information to data bus. Okay, so we have already discussed memory address register and memory buffer register. Okay, now the third and fourth are like quite similar to that of first and second. Okay, so this is IO address register and IO buffer register. We can see instead of memory, it is showing IO, right? Now let me give you an idea here first. Okay, so there is a CPU. Okay, and this CPU is actually connected to many IO devices, right? So we have a monitor, right? We have a monitor that is connected to CPU. We have keyboard that is connected to CPU. We have mouse that is connected to CPU, right? And so on. Okay, we have many things that are many IO devices that are connected to CPU. Okay, and again, a CPU like is connected to IO devices via what? Via address line, data line, and control line, right? Address, data, and control line, or system bus, right? System bus. It is connected to all the IO devices via system bus, but it is not directly connected to all the IO devices. It is connected to IO devices via IO interface. Okay, there is something called as IO interface. Okay, and each IO device, for example, IO1, IO2, IO3, uh, IO interface 2, IO interface 3. Okay, so each IO will be having one address to it. For example, A1, IO2 will have address A2, IO3 will have address A3, and so on. Okay, so each IO device will have IO interface and it will have an address. Okay, and it is connected to a common address line, data line, and control line that is connected to CPU. Okay, at the other end. Okay, now whenever CPU wants to communicate with IO devices, whenever that is the case, what it does is it sends CPU, it sends the address. For example, it wants to communicate with IO device 2. This is, for example, monitor. Okay, monitor. Okay. So if it wants to communicate with IO device 2, what it does is it will send the address A2 via address line. Okay, it will send the address A2 via address line, and this address A2 will go to all the IO devices. Okay, but what IO interface will do is IO interface will check if the address is similar to that of the IO which it is connected to. If, for example, A2 comes here, so this IO interface says this particular signal is this particular request is not for IO1. Okay, similarly, when it goes to IO2, this IO interface will say yes, this particular CPU request is for IO2, and it sends, like, it kind of uh, I mean forwards this CPU request to IO2. Okay, now these, like, if CPU wants to communicate with IO device, it sends some request, right? Now these requests are also similar to that of what we saw. It can be read request, write request, or any type of request. But one thing that is common to all the requests is the address. It needs to specify the address of IO device, right? So address will be common to all the requests. Okay, and there will be one okay, so for example, if CPU wants to send something, some data, some information, it will send the information via data line. Okay, so data or information is also sent or received from IO device or to IO device. Okay, that means a request, that means request or response, either of them can be information or data, right? Now, keeping these two things in our mind, we will look into our special purpose registers, IO address register and IO buffer register. So IO address register is used, it is showing, like you can show here, you can see here, IO address register is used to specify the address of a particular IO device, right? What does it mean? So again, this particular register or all the registers are actually present inside CPU, right? And there are some pins that are connected to the bus, system bus, right? Now this intermediate register that contains the address of IO that is sent by CPU, right? That is sent by CPU is called as IO address register. Okay, so whenever CPU wants to communicate with some IO, it will send the address of this IO to IO address register, and this IO address register will put this address to address lines, right? It will put the address to address lines. Okay, now these address lines kind of goes is connected to all the interfaces, and it will send these addresses, and the further processing will be same as we discussed. Okay, so IO address register is, again, it is a bus stop. It is a, if this is address bus, then it is a bus stop where all the addresses comes from CPU, all the IO addresses comes from CPU as a request. Okay, and while communicating, if some data is passed on, like we can see here, IO buffer register, what is it? It is used for exchanging the data. It is used for exchanging the data. That means whenever data, when let's, yeah, whenever a data comes from IO device, okay, it will come through data lines, right? Now this information will directly first come to IO buffer register, and then IO buffer register will send this data to CPU, the other parts of CPU, for processing, for further processing. Okay, so this is the task of IO buffer register. IO address register is quite similar to memory address register, and IO buffer register is quite similar to memory buffer register or memory data register, right? The only difference is we are accessing whenever we are accessing memory, we use memory address register. Whenever we are accessing IO, we use IO address register. Similar is the case with IO buffer registers, either memory or IO. Okay. Okay, so we already discussed four registers, right? What are those registers? We discussed memory address register, we discussed IO address register, we discussed memory buffer register, and we discussed IO buffer register, right? Now let's proceed our discussion with program counter. Okay, so what is a program counter? Okay, so I hope everyone remembers that when we were discussing about execution of any program, when we were discussing about execution of any program, execution of any program, then we were saying that CPU executes any program by fetching the instructions of these program, right? It fetches, CPU fetches the instructions one by one and executes each instruction sequentially, right? And when all the instructions got executed, then we say that program has been executed, right? The entire program has been executed. So this is how the execution of any program happens, right? Now counter is nothing but the counter. It is nothing but the counter that tells which instruction is to be fetched next, which instruction that CPU will fetch next. Okay, so what do I mean by that? Let me show you with an example here. Let's suppose we have this main memory here, okay, and we have this text part, okay, text part of process. Okay, it has instructions, right? So this is I1, this is I2, and so on, right? Let's take one more instruction here, I3. Okay, I3 and so on. Okay, now what CPU does is, CPU here, it fetches these instructions one by one. Okay, and we also know that whenever CPU wants to fetch the instruction, it sends the address. For example, this instruction I1 has address A1, I2 has A2, I3 has A3. Okay, now CPU will send the address A1 to MAR. Okay, now MAR will pass it to main memory, right? Main memory. Now main memory will give this instruction to MBR, right? MBR. Okay, main memory will give this instruction to MBR. So I1 is here in MBR, memory buffer register, right? And further processing will happen, right? Further processing will happen, right? Let's suppose CPU is done with instruction I1. So CPU has fully executed this instruction I1. The entire processing is now complete. Okay. So what program counter does is, there is a register program counter which stores the address of next register. What does it as address of next instruction? Sorry, my bad. So it stores the address of next instruction. So when instruction I1 was getting executed, at that time program counter consists of address 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 of instruction I2, which was the next instruction, right? So program counter stores the address of next instruction. Okay. And when this entire execution happened, I1 was like fully executed. What CPU did was like what control unit did was control unit signaled program counter to send this next instruction address of the next instruction to memory address register. Okay, so let me put it here. So let's suppose this is program counter and this is memory address register. Okay, so at time t, memory address register had address A1 and program counter had address A2. Okay, when I1 got executed, then this value A2 was shifted to memory address register. Okay, A1 was changed to A2 and now this A2 was sent to main memory. Okay, and program counter got incremented. Now the next instruction is I3, right? And the address of I3 is A3. Now program counter will save address A3 inside of it. Okay, and it waits for instruction I2 to complete. And when instruction I2 will get completed, then what control unit will do is unit will tell program counter to send the address of this next instruction that is to be fetched to memory address register. Okay, so this is how program counter sends addresses sends addresses to memory address register. Send addresses of what? Addresses of next instruction. Okay, addresses of next instruction. Okay, so what is program counter? Program counter is a register that is used to store the address of what? Of next instruction. Okay, it is used to store the address of next instruction that is to be fetched for execution, okay, by CPU. So this is program counter, and program counter is also sometimes called as, let me write it here, program counter is also sometimes called as, it is also called as instruction pointer register. Okay, it is also called as instruction pointer register. Okay, okay, so this is program counter, but again we have another special purpose register which is instruction register. Okay, you should not be you should not get confused with instruction pointer register and instruction registers. They are two different registers. So program counter is instruction pointer register and instruction register is totally different special purpose register. Okay, now let's discuss about instruction register. So instruction register stores the instructions. As the name suggests, instruction register, the register that stores the instruction, right? Now what does it mean? So so once the instruction is fetched from main memory, okay, let me show you again by diagram. So this is, for example, main memory. So okay, and okay, so this is instruction 1, instruction 2, instruction 3. Okay, and suppose this is CPU. Okay, and let's suppose this is MBR. Okay, and currently instruction I1 is fetched. Okay, that means instruction I1 will go to memory buffer register, right? I'm sorry, this is MBR. Okay, memory buffer register. Okay, now once the instruction is fetched to memory buffer register, comes to memory buffer register sends this instruction to control unit. Okay, sends this instruction to control unit, because the further processing, understanding what this instruction means, this entire part will be done by control unit. Okay, And control unit has one register which is called as instruction register. Okay, and this instruction will go to instruction register I1. Okay, this instruction will go I1 go to instruction register. Okay, now control unit will it will do is it will take this instruction from instruction register and do few things. What it will do, it will first decode it will first decode what this instruction means. Okay, then what it will do is, based on the type of instruction it is, it will generate 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 signals for all components of data path. Okay, it will generate signals for all components of data path. So first it will decode. What control unit will do is it will decode this instruction that is present in instruction register, and after decoding it will understand what this instruction means, right? And it also knows what all operations that is to be performed in order to execute this instruction, right? So we discussed this, right? Just a second. So we discussed that each instruction, for example, I1 here is nothing but sequence of operations, right? OP1, OP2, OP3 and so on, right? It is nothing but sequence of operations. So in order to perform this sequence of operations, what control unit will do is control unit will generate the signals for all the components that will perform these operations. Okay, and then it will send all these signals to all the components of data path. Okay, it will send this signal to all the components of data path. And once all these operations gets executed, then we say that instruction I1 got executed. Okay, so what is instruction register? So instruction register is a register that stores the instructions. Instruction register, this register stores instructions, and control unit will take instructions and do its processing uh, from the instruction register. Okay, it will take instructions from instruction register. Okay, and MBR will send these all the instructions that it gets to instruction register. Okay, so once instruction is fetched from main memory, it is stored in instruction register. Okay, from MBR to instruction register. Okay, instruction will go from MBR to instruction register. Okay, I hope I'm making sense. So let's continue. So now we have already discussed 6 registers, right? What are those registers? We discussed memory address register, IO address register, program counter. We also discussed instruction register, right? Only these 3 registers are remaining. Okay, stack control register, accumulator and flag register, right? Now let's discuss stack control register. Okay, let's proceed. Okay, so let's start our discussion. Okay, let's discuss about stack control register. Okay, so again let's draw main memory here. Okay, and we know that each program, when it gets executed, it is assigned a memory block in main memory, right? And this memory block is called as process. Suppose this is process P1. Okay, now this process will have multiple sections. For example, this is data section, this is text section. Okay, and text section contains instructions, data section contains global variables, etc. Okay, now it has a dynamic memory as well. Okay, and we call it as stack. Okay, let me write it here. stack. Okay, stack and heap. Okay, so stack is nothing but stack is nothing but dynamic memory, right? Sorry, dynamic memory, right? What do I mean by dynamic memory? I think you all must have read about stack in a process in operating system. But let me revise. Let me recall it a little bit. Okay. So this is stack is nothing but a dynamic memory, and dynamic memory is nothing but the memory that is a memory chunk inside the process that gets allocated and deallocated when it gets allocated and deallocated while runtime, while the program is getting executed. Okay, while program gets executed, while execution while execution. Okay, so dynamic memory is the memory that gets allocated and deallocated at runtime. Okay, and so the stack here, this stack is actually this stack, okay, inside the process. And what does this stack contains? So this stack basically contains like local variables. It contains local variables, it contains parameters to functions, right? It contains the return addresses, right? Okay, it contains return addresses. It also contains the information of another process, like this process. So for example, okay, we also know that CPU is capable of running multiple processes at a time, right? It can run P1 and it can run P2 at a time. Means it can run one process at a time, but it can do context switching, right? It can run process P1 for some time, it can then run process P2 for some time, and it does context switching here, right? Context switching. Okay. When it does this context switching, at that time the state of process is set. For example, from P1 to P2 the context switching happens. Okay, in that case, inside the memory block of this process P1, the state of state of this process is saved, right? And what do you mean by the state of process? What do you mean by state of process? State of process means like many things, right? Such as for example, if it is executing instructions, which exact instruction it was executing at last, like when it got context switched, what was the last instruction that was getting executed, right? And what is the next instruction that is that, like current instruction. Just a second, let me write it here. State can be many things, such as current instruction, right? uh, Next instruction, okay, and many more things. Okay, but all these things are actually stored in registers, right? Okay, and registers are common to all the processes, right? Because CPU has a set of registers, and all those registers will be used for process P2 as well. What happens is the values of all the registers are stored inside the stack. Okay, so values of registers, or yeah, values of registers are also stored inside stack, and this is also called as state of process, right? State of process. Okay. So this is all about stack, right? Now, what is stack control register? right? What is stack? Control register. So CPU has to keep track of what? Because this stack is allocated and deallocated while execution. It does not have anything hardwired, right? It does not have anything hardwired right now. So what a processor does is a processor maintains the state of stack. What does it mean? Since it is a stack, we also know, okay, just a minute, let me pick it and put it here. Okay, so we know that stack, what is stack? Stack is also data structure, right? And in order to access the stack, or in order to kind of manipulate the stack, we only need the top of stack, right? Top of stack. So if we have the address of top of stack, we are good, right? We will be able to access the stacks, this particular stack, right? So it can be somewhere here, right? It can be somewhere here. Let's suppose this is A1. Okay, address of top of stack is A1. Now what stack control register does is it stores the address of top of stack, right? If this is SCR, then it will store value A1. Okay, so stack control register is used to store the address of top of stack. Okay, and this is how we can this is how we can use the stack, and we can access and manipulate the stack, right? So this is what stack control register is. Okay, so I think seventh register is also done, stack control register, right? Now sorry, it is also done, right? Now these two registers are remaining, accumulator register and flag register, right? Let me tell you one thing, accumulator and flag register, both of them are inside, they both resides inside ALU. Okay, we know that there is one more hardware component called as ALU, right? It does the processing side. So accumulator and flag registers are present inside ALU. Okay, so let's discuss accumulator flag registers as well. Okay, so let's start with accumulator register. Okay, so before going to accumulator register, let's discuss little bit about ALU. Okay, we will have a discussion about ALU in details, but let's discuss a little bit about ALU. Okay, now ALU is a hardware component that is present inside data path. Okay, it is a hardware component, and we represent ALU with this particular like diagram. This diagram is the diagram of ALU. Whenever you see any diagram like this, you can just consider it to be ALU. Okay, now ALU is hardware component of data path, right? We already discussed, right? And ALU is basically used to do the operations. That means ALU supports set of operations. Okay, it supports set of operation, and these operations can be of two types. It can be arithmetic operation, or it can be logical operation. Okay, and you can see the name here itself, ALU. The full form of ALU is arithmetic and logical unit, right? The unit that can perform arithmetic and logical operations. Okay, now how does it perform the operations? So it takes two operands, operand 1 and operand 2. Now these operand 1 and operand 2 might come from either general purpose registers, okay, or they can come from directly memory. Okay, it can directly come from memory. It can come from either of them. Okay, directly memory means via MDRs, right? It can either come from general purpose register, or it can come from directly from memory cell. Now, after taking operand 1 and operand 2, based on what control unit told arithmetic and logic unit to perform. For example, we got ALU got operand 1 is 5 and operand 2 is 6. Okay, and control unit, as control unit usually sends two signals, right? First one is stating that what operation to perform. So for example, control unit is saying ALU to perform addition operation. Okay, in that case it will give the result 11, right? 11 here is result. 5 plus 6, 11. Okay, now this 11 is by default always stored in a register called as accumulator. Okay, accumulator. So accumulator is a special purpose register whose task is to store the result of arithmetic and logic unit. Okay, it is specifically designed to store the results of arithmetic and logic unit, and since it is used to store the result of ALU, it is also considered as a part of ALU itself. It is also considered as a part of ALU. Okay, so it is used to store the result of whatever operation that has been performed in ALU. Okay, now it depends what we want to do with the result, but initially the result will come in accumulator register. Okay, now the accumulator can do accumulator register can do one more thing. It can also act as an operand. Okay, let me give you an example here. So we will be discussing like types of CPU architectures in our next classes, but just to give you an idea here, there is one type of CPU architecture which is called as accumulator based architecture. So in whenever a CPU is following accumulator based architecture, there ALU will always take one operand, for example operand 1 from accumulator. Okay, what does it mean? It means that whenever control unit wants ALU to perform any operation, what it will do, it will save operand 1 in accumulator register. Okay, and then what it does is it activates this ALU and tells this ALU which operation to perform, like here addition operation, right? Addition operation, and operand 1 was 5 in our previous example, right? So control unit will first save 5 in accumulator, then it will activate ALU. Okay, then it will like take activate like it will take operand 2 from either any general purpose register or from any memory unit. Okay, memory cell, right? It will take that, and parallelly it simultaneously it will also activate ALU and tells ALU what operation to perform. So operand 2 comes from either general purpose register or main memory, and operand 2 and operand 1 will come from accumulator itself. Okay, and again the result will be saved in accumulator. So the result, as soon as ALU performs any operation, accumulator gets accumulator accumulator gets rewritten. Accumulator gets rewritten. Okay, that means accumulator was first storing 5, and as soon as ALU performed 5 plus 6, now the recent value that accumulator stores is 11. Okay, this means that accumulator can store two things, right? It can either store operand or it can store result. So it will definitely store, this is definite, it will definitely store result, but depending on the architecture of our CPU, it can also store operand. This is optional. Okay, so we can see the definition here. Accumulator is located inside the ALU and it is used during arithmetic and logic operations for storing what? For storing the result. Okay, so this is accumulator register. Okay, there is one more register that is present in ALU. What is that? Right, flag register. Okay, the name of that register is flag register. We also say flag register to be program status word. There is another name for flag register which is program status word. You can also see this name instead of flag register. Okay, it is also like in short, uh, like it is represented as PSW. Now PSW, what is PSW? As we already discussed, like accumulator register was storing the result of ALU, right? So accumulator register was storing what? It was storing the result of ALU, right? Result. Now what flag register stores is flag register or program status word. It stores the status of that result. Okay, it stores status of value present in accumulator, that is the result, right? It stores the status of result. Now what do you mean by status? What is status of register, right? This might be the question. Okay, now flag register is having multiple binary cells, right, as any register. Okay, and each binary cell is associated with one flag. Okay, for example, this is a sign flag. Okay, let's suppose this is a sign flag. Okay, this is flag register and this is a sign flag. First, the binary cell with index 0 is a sign flag. What does it mean? It means that whenever the value inside the sign flag is 0, right, in that case it is stating that accumulator register or the result is actually positive value. Okay, that means the result is positive value. And whenever the sign flag is 1, in that case it is stating that the result is negative value. The result is negative value. In similar manner, there are different indexes there are different indexes that are assigned to, sorry, let me take the same pen. Okay, there are different indexes that are assigned to different flags. Okay, so there are certain flags that represent the status of this register, right? Like status of this result. So result being positive or negative is the status of this result, right? So these type of statuses are represented as a flag. It can either be 0 or 1. Okay, so this flag, like the each flag here has only can have only two values. It can either be 0 or it can be 1. It stores the boolean value. Okay, it stores the boolean value which can either be set or reset. Okay, set means something and reset means something. Okay, this is set, this is reset. Okay, now the question is like what all different flags are present inside the flag register, right? Okay, let's take that question. Okay, so there are basic two types of flags in a flag register. Okay, there are two types of flags. Two types of flags. Okay, in flag register. Okay, one is control flag. Okay, and another one is conditional flag. Okay, another one is conditional flag. So control flag is actually not like in our use, like we don't require control flag as per the gate. Okay, if we want to, like, we can study this, but like since it is not relevant with gate point of view, we won't be discussing this too much. Let me give you few flag names here. You can just search it out and you can just read it, but I mean, there is no need to put extra effort in these particular flags, control flags. Okay, let me give you the name here. So there is one flag which is called as interrupt flag. Okay, there is one flag which is named as direction flag. Okay, there is one flag named as trap flag. Okay, so these are like three control flag examples. You can search them on Google, you can read them out, but don't waste your time too much on these flags. Okay, so conditional flag are the flags that are actually asked in gate. Okay, so we'll be studying conditional flags. So what are different type of conditional flags here? So we have carry flag, we have carry flag, we have auxiliary carry flag, auxiliary carry flag, auxiliary carry flag. We have parity flag, we have overflow flag, we have sign flag, and we have zero flag. Okay, these are six important flags that we'll be studying. Okay, let's take each one of them in sequence. Let's start with carry flag. Okay, we will discuss all these flags using example. Okay, so let's take one flag register. Okay, let's take one flag register. Let's consider each all the register to be of size 1 word. Okay, so this is 8-bit flag register. Okay, let's suppose there are these 6 flags that are residing inside this 8-bit flag register. Okay, and since obviously 6 is less than 8, therefore we are excluding the first and last binary cell. Okay, now what we will do is from index 1, I'm sorry, from index 1, 2, 3, 4, 5, 6. Okay, 5, 6, 7. Okay, so from index 1 to 6 we are having all these flags. Okay, let's also name these flags. Let's name this flag as carry flag. Okay, so index 1 is for carry flag, index 2 is for auxiliary carry flag. Okay, index 3 is for parity, index 4 is for 0, index 5 is for sign. Okay, and let's suppose index 6 is for what is it meaning, overflow. Okay, oh, sorry, overflow. Okay, now let's proceed with our examples. Okay, so let's start with carry flag. Let's see what it is. Okay, again, so what it does is carry flag, sorry, this flag register saves the status of the result present in accumulator, right? And what is the result? Result is of an operation, right? Result is of an operation, right? Let's suppose this is an operation. Okay, we are performing some operation, ALU is performing some operation, and let's take two operands here. Let's take operand 1 as 100 10001. Okay, let's take operand 2 here as 1001001. Okay, let's suppose the operation that is to be performed by ALU is addition operation. Okay, addition operation. How do we do this addition? I hope you all know how to do this addition over binary sequences. Okay, now this 1 plus 1 is 2, right? How do we represent 2? 1 0, right? 0 will go here, 1 will go here. Now 1 plus 0 plus 1, again it is 2, right? 0 go here, 1 go here. 1 plus 0 plus 0, it is 1, right? Now we'll put here. Now 0 plus 0 is 0, we'll put 0 here. 1 plus 1 is 2, therefore 0 here and 1 here. 1 plus 0 plus 0, it is 1. 0 plus 0, it is 0. And 1 plus 1 here is 2, right? What is it? 0 and 1, right? Because it is carrying. Okay, so you all must have noticed here the operands that we had were of 8 bits in size, right? 8 bits in size. And we have already uh, considered all our registers to be of one word or 8-bit size. Okay, sorry, we are considering one register to be, yes, 8-bit size. Okay, 8-bit size. Okay. Now we can see here, after the addition operation, we are getting 9 bits, right? Now we can't store 9 bits in 8-bit register, right? Accumulator will also be an 8-bit register, right? Accumulator will also be an 8-bit register, right? Now what we will do? What should we do? So what we do is we save this part, okay, the part starting from index 1. This is suppose index 0, starting from index 1 to till the end. We will save this part, sorry, this part in our accumulator register. Okay, and we will take this part and we will save this part in flag register. And where we will store this value? We will store this value in index 1. What is index 1? Index 1 is carry flag, right? We will store 1 here. Now carry flag, whenever it is 0, this means that the value stored in accumulator is not a whole value. Okay, sorry, it is a whole value, right? If the carry flag is 0, that means the actual value, actual result was 8-bit result. Okay, and whatever present in accumulator is actually the entire result. Okay, that means no carry, no carry was present. But if carry flag is 1, that means there was one carry, and actually the result was not 8-bit but 9-bit result. Now this 1-bit result, 1-bit, that is 1, should be added in front of the value that is stored in accumulator in order to use it further. Okay, so this is how we know whether the result stored in accumulator is either 8-bit value or a 9-bit value, right? Okay, so now let's discuss about auxiliary carry flag. So what is auxiliary carry flag? So auxiliary carry flag is set if fourth bit contains a carry. What does it mean? It means that whenever there is a carry that is from lower nibble to higher nibble, in that case we say the auxiliary carry flag is set. Again, I think this is quite like you must have not understood it, right? Let me give you an example here. I hope everyone knows nibble, right? What is nibble? So nibble is 4 bits, right? Whenever we do this BCD arithmetic, we encounter nibbles, right? We represent each decimal with a nibble, right? And we require like okay, for example, we are doing some addition operation, right? OP1 and OP2. Let's take operation operand 1 and operand 2. Okay, so let's take operand 1 as 0, 1, 1, 0, 1, 1, 1, 0. Okay, let's take operand 2 as 1, 0, 0, 0, 1, 1, 1, 1. Okay, so okay, let's do addition operation here. Okay, let's do addition operation here. 0 plus 1 is 1, 1 plus 1 is 2. Okay, 1 plus 1 plus 1 is 3. 3 is represented by 1 1, right? Therefore it is 1 here, 1 here, right? Similarly 1 1 1 is 3, right? 1 here and 1 here, right? Again this is 1, this is 1, this is 1, and this is 1. Okay, now one thing that you can see here is, if we divide each operand into nibbles, what we can see here is this 0 1 2 3, right? Third binary cell, when we do addition over third binary cell for both the operands, we are getting one carry here, right? So when we get one carry from third bit, fourth bit to fifth bit, right? In that case, we say auxiliary carry flag is set. Okay. Therefore, whenever auxiliary carry flag is 0, that means there is no carry. There is no carry from no carry from. Let's represent them as D1, D0, D1, D2, D3, D4, D5, D6, and D7. Okay. Now there is no carry from D3 to D4. Okay. There is no carry from lower nibble to upper. There is no carry from lower nibble to upper nibble. This is lower nibble, this is upper nibble, right? Whenever auxiliary carry flag is 1, that means there is one carry from D3 to D4. Right? There is one carry from lower nibble to upper nibble. Okay? And it was being represented like carry flag was assigned to which index? Yes, index 2 was representing auxiliary carry, right? So this value goes here. Okay, so this is auxiliary carry. So what is this D0, D1, D2, D3? They are nothing but a way to represent the position of bit. Okay, and what is this one coming from lower nibble to upper nibble? This is nothing but, like we already saw, right? 1 plus 1 is 2, right? 0 is here, and it was actually 2, right? Which is 1 0. So we can certainly say that one bit was carried from, let's suppose this is D0, this is D1. We can say that one bit was carried from D1 to D2. Okay, similarly here we saw one bit was carried from D2 to D3. Okay, then one bit was carried from D3 to D4, right? This. Okay, whenever there is one bit that is carried from D3 to D4, we can also say that one bit is carried from lower nibble lower nibble to upper nibble, right? And therefore, whenever this is the case, we make this flag as set. Okay? We make this flag as sorry, 0 1. We make this flag as 1. Okay. Set reset we can like do nomenclature accordingly, but we will put value 1 here. Okay, we just whatever carry we are doing from d3 to d4, whether it be 0 or 1, whatever value it is, we just directly take this value and we put this value in auxiliary carry. Okay, this is AC and this is carry flag. Okay. So the carry from D3 to D4 is also called as auxiliary carry flag. Okay, I hope I'm making sense here. So let's proceed. Let's now discuss about parity flag. So parity flag is generally used for error detection. Okay, it is used for error detection. Okay, now what is a parity flag? Whenever a parity flag is set to 1, this means that number of ones in result is even. Okay, so what do I mean by that? Let me give an example here. Okay, let's suppose this is an accumulator register and the result here is 110, 110 and 11. Okay, now let's count the number of ones. 1 2 3 4 5 and 6, right? So there are 6 ones, right? There are 6 ones and 6 is even, right? Now in that case what we will do is we will set parity flag as 1. Okay, we will set parity flag as 1, which basically says the number of ones in result is even. Now what is I mean, it is quite obvious, but when do we set parity flag as 0? It is set as 0 when number of ones in result is odd. Okay. When number of ones in result is odd. Let's suppose in the same example, let's erase one bit here. Okay. Let's take this bit to be 0. Okay. In that case, now we have 5 ones, right? And 5 is odd, right? So now the parity flag will be what? Now the parity flag will be 0, right? Now you might be having this doubt like how this parity flag can do this error detection, right? How is it helpful when we try to do this error detection in our result, right? Okay, let me give an example here. Let me take two scenarios here. Okay? Let's let's take two scenarios here. So scenario one says, okay, let me first erase this part. Okay. Okay, so let's take an example here. Okay. Scenario one. Let's suppose we have value 11001011. Okay. This value is stored in accumulator register. Okay. Now we can see that 1 2 3 4 5, there are five number of ones, right? Now it is odd, right? So for this particular scenario parity flag will be 0. Okay, now let's take scenario 2. Let's take scenario 2. Sorry, scenario 2. Okay, in scenario 2 let's take the value of accumulator as this. Okay, let's suppose this is accumulator register and the value of accumulator register is this. Okay, now what we can see here is the number of ones here is 4, right? And 4 is even, right? Now the parity flag will be set to 1. Okay, now let's suppose due to some voltage spike, there is the value that is stored within the accumulator changes. Okay, and it changes by 1 bit. Okay, it changes by 1 bit. It changes by 1 bit. Okay, in both the scenarios one spike happens, and due to that spike 1 bit is, for example, in scenario 1 the bit is this, in scenario 2 the bit is this. Okay, and this bit changes. Okay, it toggles, right? So what will be the case? The case will be, for scenario 2 0 will become 1, right? So there will be addition of one more 1, right? That means there will be, instead of 4 there will be 5 ones now, right? But we know that parity flag is already 1, right? Now there is discrepancy, right? now we have detected Now we have detected that there is some error our in our accumulator, right? There is some discrepancy. So either one of these bits are wrong, right? Similarly, here this 1 will become 0, right? The number of 1 will change. Now the number of 1 will be 4, right? So if number of ones are 4, then it is even, right? So parity flag should be 1, but it is not, it is 0. Therefore there is a discrepancy, and in scenario 1 as well we have detected the error. Okay, okay, so in scenario 1 and scenario 2, in both the cases one of the bit will toggle, right? And due to the change of one bit, the count of zeros and the count of ones will change by one number, right? It can either be +1 or -1, right? So if there is a change of only one number, like either it can be +1 or -1, then the value will, if the value is odd, it will become even. If the value is even, it will become odd. In both the cases, we are able to detect, right? If it is getting even after odd, we are able to detect it. If it is getting odd after even, we are able to detect it, right? So in both the scenarios, we are able to detect the error, right? Now the question might come, like, let's suppose in the spike parity flag also changes. Okay, parity flag also changes from 1 to 0, right? Now that is a valid question, that might happen, but again, if you see the probability here, the probability of changing this bit, the bit getting changed, uh, the probability of one of 8 bit getting changed is high, right? But the probability of just one bit out of many getting changed is very low, right? That is why we generally assume that our parity flag has not changed. So all these error detection will happen based on the assumption that our parity flag is like our parity flag remained intact. It has not been changed. Okay, if it is also changing and this is not changing, in that case there is a discrepancy, right? In that case also we have detected the error. But if both are getting changed and they are getting changed in such a way that both are now like there is no discrepancy between these two, even after changing, even after the changes, in that case we won't be able to do the error detection. Okay, so this is like a very the probability of this happening is very low. Okay, so this is parity flag. So I hope I'm able to communicate parity flag. Let's proceed with zero flag. Zero flag is quite simple. Zero flag is set to 0 when the value of accumulator register is non-zero. Okay, when value of accumulator register is non-zero, okay, and it is set to 1 when value of accumulator register is set is 0 is 0. Okay, so if we have accumulator register here and value is 0, right, in that case zero flag will be what? Zero flag will be 1. Okay, and if not, if either one of the bit is 1, in that case zero flag will be 0. Now the question that you should be asking yourself is, where do we use this zero flag? So where exactly is this zero flag used, right? So let's discuss a little bit about that as well. Okay, so zero flag is basically used in conditional or jump instruction. Conditional or jump instruction. Okay. So you must have seen, so you might have written some code, right? And you must have uh, either heard about or seen somewhere like written something like this: if x is equal to 0, do this, else do this, right? Now this do this is itself like set of like sequence of instruction, but you are getting my point, right? So this if condition you must have seen somewhere, right? Now these if conditions are actually implemented using this zero flag. How is it? Let's discuss. First of all, let me tell you that this if instruction, when it is converted to something like assembly code, so assembly code is nothing but kind of like a high level representation of like an English representation of sequence of bits. Okay, the instruction that we are talking about. Okay, so if we have some sequence of instruction, the readable format of this sequence of instruction will be assembly code. Okay, now this if condition will always have two instructions. Let's suppose I1 and I2. Okay. So we represent this if x is equal to 0 as load into accumulator x and jump if 0 to instructions, let's suppose I8. Okay, so what does it mean? Okay, let me first make this example totally. Okay, so this is I8 and so on. Okay, now whenever this part is converted to assembly language or like machine code, instruction will look something like this. Okay, if x is equal to 0, this will be this part. Okay, now when we execute this, what happens when instruction 1 gets executed? In that case, our CPU will load value x into accumulator, right? Accumulator. So now this x will be the result for us, right? And since flag register contains the status of values inside accumulator, so flag register will have things, the flags with respect to this value x, right? Now there is another instruction which is jump if 0. This jz means jump if 0. What does it mean? So as soon as instruction I2 comes inside like CPU, what control unit does is control unit sees that it is JZ, right? Jump if 0. So control unit checks the checks the zero flag. Okay, it checks the zero flag. Zero flag states whether the value of value present inside accumulator is 0 or not, right? If x is 0, then value here will be 1, right? And if value here is 1, what it will do is it will change. For example, this is control unit. So control unit is sending, I2 came to control unit, and control units checked this flag register, and it checked if this 0 flag is 1 or not, and suppose it is 1. In that case, what control unit will do is it will change program counter. What was program counter? Program counter was the address of the next instruction, right? And here in this I2 we have the address to next instruction, right? This states that if x is equal to 0, run this part, right? Run this part. So the starting of execution of this sequence will be present here, right? For example, the if section is from I8 to I12. Okay, this entire section is what? These are instructions under if condition. Okay, and let's suppose from I3 to I7, this part is actually instruction under else condition, right? So first of all, it checks, control unit checks if 0 flag is a 1 or not. If it is 1, so initially program counter, since it was like running instruction I2, it was having address of I3, right? So it will change this value. It will change this value and change this value to address of I8, and this address of I8 is actually present inside instruction, right? So control unit will know where exactly uh, do we want to jump our execution, right? So control unit will take the address from instruction itself, and it will put this address to program counter. Okay, so in this way, like our next execution will be of instruction I8, and so on. It will run this till I12, and then it goes on. Okay, so let me write it here as well. So this control unit, what it will do, will check 0 flag and change program counter or PC, sorry, to address of next instruction. Okay, next instruction accordingly. Okay, accordingly means if the 0 flag is 1, then address of next instruction will be address of instruction 8, else it will remain address of instruction I3. Okay, so I hope now, like you're having an idea why this 0 flag is being used, right? Okay, so let's proceed our discussion. Let's discuss sign flag and overflow flag. Okay, so let's start with sign flag. So before discussing sign flag, let me tell you that this flag has relevance. This flag has relevance only when the value that is stored in accumulator register is actually a signed integer. Okay, it is only relevant when the value that is stored inside this accumulator is a signed integer. So what do we mean by signed integer? So we will have a very detailed discussion on signed integer when we will be discussing about the format of data values. But for now, like just understand it in this way. Okay, integer. Whenever we want to represent an integer can be represented in two ways. Okay, signed integer and unsigned integer. Okay, whenever an integer is represented in binary sequence, it can be either represented as a signed integer or it can be represented as an unsigned integer. So what do you mean by signed integer? So signed integer will support positive as well as negative integers, right? We can represent plus 14, we can represent minus 14, both, right? But in unsigned integer, by default, only positive values can be represented, right? We will say 14, that just means that it is plus 14. Okay, there is no provision to uh, represent any negative value in unsigned integer. So when we discuss about sign flag is only relevant when we are saving, or when we are putting the value, the value of integer that is represented in signed integer format. Okay, signed integer is nothing but a format in which we kind of represent any number, any value, right? So let's suppose this is an accumulator. Okay, and we want to put x is equal to 14 here. Okay, let's suppose we want to put x is equal to minus 14 here. So only way to put x is equal to minus 14 here, or the value minus 14 here, is to put it in a signed integer format. Okay, so okay, I think signed integer, you must get a little bit about what signed integer is. So the only thing that you need to understand here is that whenever we represent any signed integer, let's suppose this is a binary sequence which is representing any number. Okay, the only thing that you must be understanding here is the first or the most significant bit, MSB, will always be reserved. Let me write it here. Will always be reserved to represent the sign. Okay, whenever we are representing, okay, sorry, whenever we are representing any integer here in signed format, the most significant bit will always be reserved to represent the sign. Okay, and how is it put? Whenever the most significant bit is 0, it means that the integer is positive. Okay, and whenever the most significant bit is 1, this means that the integer here is negative. Okay, integer that is saved inside the this accumulator register is 0. Sorry, negative, I'm so sorry. Okay, integer is negative. Okay, now when we have a value stored in accumulator and that value is signed integer, right, then it means that there is a sign to it, right? That means this value can be either positive or negative, right? And we know that in order to check the sign of this integer, right, we can see the most significant bit and we will get to know the sign of this integer, right? Therefore, sign flag is nothing but a flag that is set to 0 when integer is positive, right? Which also means when MSB is 0, right? And it is set to 1, sign flag is set to 1 when integer that is stored in accumulator register is negative and most significant bit is equal to 1, right? So as simple as that, right? Sign flag is set to 0 when the integer that is present inside this accumulator register is positive, and it is set to 1 when the value that is present inside accumulator register is negative. Okay, now the first or the most significant bit represent the sign, and the remaining part in signed integer, we are talking about signed integer only, right? So the remaining part will represent what it will represent. It will represent absolute value. What do we mean by absolute value? We mean mode of x. If we are representing x here, if we are storing x here, and x can be either positive or negative, the the number of binary cells that we will be using to represent the absolute value will be, let's suppose the size of this accumulator is y, then the number of binary cells that we will be using to represent the absolute value will be y minus 1. Okay, let me give you an example here. Let's take an example of minus 14, the same example. Okay. Now if you want to represent minus 14 uh, in signed integer format, then accumulator will look something like this. Okay, let's leave this MSB and let's represent minus 14. How can we write minus 14? Minus 14 can be written something like this, right? 1 2 2 plus 4 6 6 plus 8 14, right? So this is 14. Okay, and if this is 8 bit, let's suppose this is 8 bit. Okay, so this is 7 bit, right? This is 7 bit, right? So this is 1 2 3 4, 1 2 3 4 0 0 0. These are 7 bit, and since it is 14, we will put 1 here. Okay, now 1 0 0 0 1 1 1 0 represents minus 14. Okay, and whenever this is my plus 14, whenever it is plus 14, let's take another page. Okay, let me insert one more slide here. Okay, and okay, just a minute. Yes, and whenever we want to represent plus 14 here, how can we represent that? Again, all the other thing will be same: 0 1 1 1 0 0 0, right? And this most significant bit will be 0. Okay, for minus 14 it will be 1, and plus and for plus 40 it will be 0. Okay. So sign flag is used to represent the sign of a value present in accumulator register. Okay, okay, so the last flag that we will discuss here is overflow flag. Okay, similar to the sign flag, overflow flag will also be relevant only when the value present in accumulator register is signed value. Okay, if the value is signed value, integer is signed integer. Okay, so sign flag as well as overflow flag, both of them are relevant only when the value that is stored inside accumulator is signed integer. Okay, and overflow flag is actually a signed integer version of version of carry flag. Okay, this works exactly as carry flag. Okay, but since here one signed or most significant bit is kind of uh, uh, like already reserved to represent the sign, carry flag won't work in a similar manner, right? We can't just take the remaining bit as it is for carry flag. Okay, for overflow flag. Okay, so how is it, like, how signed equivalent of carry flag, how is overflow flag the signed equivalent of carry flag? Let's discuss that. Okay, so carry flag basically gets raised when the result of operation can't be stored in accumulator register, right? So what do I mean by that? You must have remembered, like, when we discussed carry flag, we discussed that after the operation the result was actually 9-bit value, but since the accumulator register was actually 8-bit register, therefore we were not able to put 9-bit value into 8-bit register, right? And due to that we raised carry flag, right? We raised carry flag which represented that that the value is not in the range, right? The value is not in the range of representing range that can be represented using only 8 bits. Okay, not in the range. Similarly, overflow flag also works. So overflow flag, it is set, it is set to 0, sorry, it is set to 1, it is set to 1 when or if not in range. This means after the operation, the result actually can't be represented using 8-bit register. Okay. In that case, it is set to 1, and overflow flag is set to 0 if value in range. Okay. So what do I mean by that? And what is the range of an accumulator register when the signed value are put into it? Let's discuss a little bit about that as well. Okay, let me make this. Okay, so when we were discussing about carry flag, right? When we were discussing about carry flag, what we had was unsigned integer, right? So since it was unsigned integer, it started from 0, right? And up to certain value we were able to represent, right, or store into 8-bit register, right? Able to store, okay, in 8-bit register. And after this, when the value got bigger, after this, after certain threshold, when the value got bigger, this was totally not in a range part, right? Okay. Similarly, when we see overflow, okay, overflow is little bit different, right? Because it the value that is stored in accumulator does not start from 0 and only goes towards positive. It also goes towards negative, right? So when we represent it on the number scale, it looks something like this. Okay, starting from 0, we can represent up to certain point. Okay, and for positive we can represent up to certain point. This side is positive, this side is negative. Okay, up to certain point we can represent in positive, and up to certain point we can represent in negative. Okay, and after that, this part and this part, both these parts comes under not in range section. Okay, both these parts comes under not in section range. So let's suppose we had this 8-bit register. How many numbers can we represent using 8-bit register in case of unsigned integer? When it is unsigned integer, in that case, what is the range? It will be 0 0 2 to what? 2 to the power 8 minus, sorry, 8 minus 1. It will be 0 to 2 to the power 8 minus 2 to the power 8 minus 1. Okay, because there are 8 bits, right? And if we are starting, therefore we can totally have 2 to the power 8 numbers, right? And if our count starting from 0, the count will go till 2 to the power 8 minus 1. Okay, and after that we won't be able to represent the number, right? Not in range. Now if you want to see the same thing with overflow situation, that means if we are putting signed integer, right? So how many numbers can we represent here? Like let's suppose we have accumulator register with again the 8-bit registers, right? 8 bit value. Okay, we have binary cells, 8 binary cells in our accumulator register. So how many numbers can we represent? One is for sign, right? We can't use that. So we have 7 remaining bits. Okay, and using these 7 remaining bits, what we can do is we can represent 2 to the power 7 numbers, right? Now this 2 to the power 7 numbers can be positive and can be negative, right? So the first thing that will come into your mind is we can represent 2 to the power 7 here and 2 to the power 7 here, right? But it is actually not the case. Okay, so what is the case? Now you must see here, this 2 to the power 7 will also have one value as 0, right? But we don't have two values, plus 0 and minus 0, right? So we have one remaining representation, right? Let's suppose we have 0 0 0 0 0 1 2 3 4 5 6 7 1 2 3 4 5 6 7. Okay, we have 0 0. This is the absolute value. So the two values can be there, 1 remaining 0 or 0 remaining 0, everything 0, right? Both will represent 0, right? So what is the use? It is kind of like redundant, right? So in that case, what we can do is we can consider 0 to be positive, okay, and we can represent one extra negative value, okay, one extra negative value. So if we consider 0 to be positive, in that case the value will go till 2 to the power 7 minus 1, right? And if there is one extra number that can be represented, therefore it will start from minus of 2 to the power 7, right? Therefore the range will be from minus 2 to the power 7 to plus 2 to the power 7 minus 1. This will be the range, okay? If our value, or the value that is stored in accumulator, or the value that is kind of like calculated after the operation, the value that is being generated, this value is between this minus 2 to the power 7 to plus 2 to the power 7 minus 1, then the value, then the sorry yeah, then the value inside overflow flag, right, it will be 0, else it will be 1, right? If it is not between if the resulted value is not within this range, the value overflow flag will be set to 1. Okay, I hope I'm making sense here. So these are 6 conditional flags that we discussed. We have discussed all of them. Okay. Overflow and snag. Right. So let's proceed with our discussion. Okay. So all the special purpose registers are already covered, right? Let's see. Yes, we have discussed accumulator register and flag register. We also discussed different flags that are present in different flags that are present in flag register, right? So we are good here. We discussed all the special purpose registers. We know a little bit about general purpose register. They are actually not like they're additional registers that we can use, that CPU can use on the go. Okay, and we have some nomenclature for that, and we follow that nomenclature, R1, R2s, and so on. Okay, so our discussion for register is complete. So one hardware component is complete in data path. Now let's proceed with another hardware component, right? Let's go on to arithmetic and logic unit, or ALU, right? Now ALU is also a hardware component of data path, right? Hardware component of data path. Now what does it do? It does arithmetic and logic operations. It is used, or it is capable of performing, it is used to perform what it is used to perform arithmetic and logical operations, right? Arithmetic and logical operations, computations, operations. Let's write it computation. Okay. It is used to perform arithmetic and logic computation. Okay. We already saw a little bit about arithmetic and logic unit, right? We represent ALU using this diagram, right? This diagram. Okay. Arithmetic and logic unit takes two operands, OP1, OP2. It saves its result in accumulator register, right? And it has one register which is known as flag register that is used to store the status of accumulator register, right? Store the status of accumulator register, right? Status of value inside accumulator, value inside accumulator. Okay. Now since this is a hardware component, we will be having two lines that are coming to this hardware component from control unit, right? Control unit, the manager, right? Control unit will tell two things, what and when, to ALU, right? And what is represented using operation code. So what is operation code? Operation code is is nothing but, like, okay, so we have some sequence of operation, that sequence of computation that can be performed using ALU. Okay, so ALU can perform, it can perform multiple computations. Let's say operation. Okay, operation can perform multiple operation. Okay, one at a time, but it can perform multiple operation. We have, like, so ALU can perform addition, it can perform subtraction, it can perform and or not, right? And or not, and so on. But it can perform any one of them at a time. Okay, one at a time. Okay. So which operation to perform will be told by control unit here. Okay, control unit will say perform operation addition. Okay, perform addition, perform addition. Let's take an example here. Okay, perform addition. And when control unit wants to say, like, wants this operation to be performed, it will activate this ALU using select line. Okay, select line is telling when, right? It is telling when. So whenever control unit wants to use ALU, it will first activate ALU using select line, and then it will send this operation code which tells which operation to be performed. Okay, so since ALU can support a set of operations, so we actually have the number for each of these operations. Let's suppose ALU can perform 8 operations. Okay, let's suppose it can perform 8 operations. So what happens is these 8 operations can be represented using how many bits? Log 8, right? Log 8 base 2, that is 3, right? So when we want to represent 8 operations, it will look something like this. 000 is plus, 001 is minus, 010 is and so on. Okay. So what is this operation code? So control unit will again send this particular thing, which is 3-bit information, right? And this 3-bit information will tell which operation to perform. Okay, whether it be addition, subtraction, or whatever, right? Let's suppose 000 is addition, right? So in that case, control unit will send something like this, 000. Okay, and this 000 will go as operation code here. Okay. Okay, so this is ALU, And like ALU is basically, we also say arithmetic and logic unit as mathematical brain. Mathematical brain. Why? Because it does all the computation. So like we also saw registers, right? A register was used to write or store uh, the values, right? The binary sequences. But what is the use of those binary sequences? We basically require them to like being like we what we do, what we want. Our main goal is the computation over the data, right? Manipulating the data in certain way, right? Such as addition, subtraction, and so on, right? So this manipulation of data is actually done using arithmetic and logic unit. Therefore, it is called as mathematical brain of computer. Okay, mathematical brain of CPU. Now, like if we understand the fundamentals of ALU, then we'll be able to see like how the computations happens, right? So let's look into that. Let's start looking into that. Since we know that it can perform arithmetic and logic computation, so let's see what it means. So ALU is basically a digital circuit, right, that contains many things. Okay, many things. Since it supports many operations, it contains the logic for many operations, right? And these computations or these operations are basically classified into two types: arithmetic operations and logic operations. Okay. So we can like virtually or like logically divide this entire ALU. Let's suppose this is ALU. Okay, we can divide this entire ALU into two units. Okay, not physically but virtually or logically we can divide into two units. One unit that is capable of performing arithmetic operations, and one unit that is capable of performing the logical operations. Okay, now what are the different arithmetic operations? Addition, addition of two numbers like x plus y, subtraction of two numbers like x minus y, right? X minus y. Increment operation like x plus 1, right? Decrement operation x minus 1, right? Negation operation minus of x, right? All these things can be performed using arithmetic unit. Okay. Arithmetic unit supports these operations. Okay. And logic unit, these units are used for logical operations. This unit is used for logical operation. The logical operations is and, or, XOR, not. This not is actually bitwise not. Okay, bitwise not. So you must be having this doubt. The negation is done using arithmetic unit and not is done using logic unit. What is the difference, right? Now this not is actually bitwise not, and negation is negation, okay, of an entire number. So let's suppose we have a signed integer, right? Let's suppose you have 0 0 0 0 1. Let's suppose this is the, and since we discussed like signed integer represented by like putting the sign in the most significant bit. Let's suppose this is 0. Now what does it mean? It is plus 1. If we want to negate, what we can do is we can just change value here. Okay, so this is 1 0 0 0 0 and 1. Okay, one of the representation is this. Okay, one of the representation of minus 1 is this. Okay. So this is negation. Okay, what is not? If the value is 0 0 3 4 5 6, value is this, then it will do bitwise not. Okay, for each bit it will just toggle the value. It will be this 0 to 1 0 to 1 0 to 1 0 to 1. Okay, so what you can see here is actually bitwise not. What's happening here is whatever is coming here, it goes through not this gate, and the value again goes here. Okay, so the bit that is coming, the toggled value of that particular bit will go out. So this is one way of negation. Okay, let me clarify a little bit. So this is one way of looking into negation. Okay, there might be the case that this value is not minus 1. Okay, there are some formats where this value is actually not -1. What will be in that case? Okay, let me delete this. In that case, again it is very simple. Okay, what is, if we want to negate x, let's suppose we have x value x. If we want to negate x, what we will do, we will use subtraction. Okay, how we can subtract x with x, right? We will get 0, right? Then we will, what we will do, we accumulator will store 0, right? Now again we subtract it with x, right? What will, what accumulator will store will be -1 minus x, that is the negation of x. Okay, we can directly store negation of x by just subtracting 0 with minus x, 0 with x, right? In that case, the value that is stored inside accumulator will be minus x, right? So using subtraction once or twice, both variations are here, we can implement negation. Okay, so yeah, I think I'm making sense here. So let's proceed our discussion. So okay, one thing is like remaining here, numerical checks, right? So the numerical check is actually nothing but the checks that are something like uh, whether a number is 0 or not. Okay, these type of checks are called as numerical checks. Okay, and we usually fill our flag registers, the flags in flag registers, using these numerical checks only. Okay, so these numerical checks are something, look something like this. Okay, if we change it with the value inside accumulator, then it will be like something like this flag register, right? The flag in flag register, 0 flag in flag register, right? So okay, so I think we have covered all the operations here. There are many more operations actually. We can see here shift left, shift right operations as well, right? XOR, or, and, not, shift right, shift left, add, right? So so what is shift left, shift right? Let's discuss a little bit. So shift left and shift right, shift left and shift right. Uh, okay, so first of all, let me tell you this, that we will be discussing shift left and shift right again when we will be discussing about the data formats. Okay, data formats and number representation. For now, you can just assume, like you can just understand it in this way. Okay, let's suppose we have a number here, a binary sequence here, which is a value. Okay, let's suppose 1 1 0 0 1 1 0. Okay, one, let's take one more. Okay, so this is a number, this is a value. Okay, now when we do shift left, it means we shift each bit of this number uh, towards left, one bit towards left. Again, actually this shift left has two parameters. One is the value, let's suppose the value is x, and the other parameter is the number of bits that we require it to shift. Okay, let's suppose for now it is 1. Okay, so we will be shifting each bit towards left by 1 bit. Okay, what do I mean by that? This means that this 1 will go here, this 0 will go here, this 1 will go here, and so on. Okay, so this one now will not be here, this will not be here. Okay? And we will be having the last number is 1 here. Okay, and 0 0 here, sorry, 0 0. Okay, let me write it correctly. So the first number will be, first bit here will be 1, then two zeros, then two ones, and so on. Okay, so these are 7 bits, right? Now the 8th bit here, we will directly put 0 here. Okay, we'll put 0 here. So this is like an extreme condition where the extreme bit is 1. But if the extreme bit is not 1 but 0, okay, in that case, so if extreme bit is 1, we will be having one carry here, right? We will store this in carry flag, right? But so we are talking about this value present in accumulator, okay? Because after this shift left or shift right, the value will go to accumulator, right? Because this is a part of ALU. So after the operation, this will go to carry flag, okay? Now the another thing is, let's suppose the value here, the last bit was not, so this is actually operand, okay? Let me put it this way, just a second. Yes. So this is not actually the value inside accumulator, this is the operand, okay? This is operand, okay? This is operand 1, operand 1. Now operand 2 is 1, right? Shifting by 1 bit, right? This is operand 2, okay? Now this value is the value inside accumulator, okay? And when we shift uh, each each bit by this number of operand 2 number of bits, the remaining the there will be some slot that are left blank in the right. We what we do is, in this shift left we put, let me write it here, we put zeros in in rightmost blank spaces, okay? We put zeros in rightmost blank spaces. What does it mean? So what is the relevance of shift left? Let's discuss that. I think you must be having an idea what the values represent, because it is a binary sequence, right? Therefore, if whenever we want to do the multiplication of this number, of a number, let's suppose there is a number called x, and we want to do multiplication of x by 2, right? In that case, we will see that our binary sequence will be like, if this is a binary sequence for x, we will add 1 0 here, and this will represent x into 2, 2x. This will be 2x, okay? And this is shift left is basically used to implement the operation x into 2 to the power of operand 2, okay? Now this x is actually operand 1. Let me write it here as well. Instead of x, we can put it as this operand 1 into 2 to the power operand of operand 2, okay? So this is the operation that is being performed when we do shift left, okay? Shift right, you must be getting the idea. Instead of multiplying, we are dividing by 2, right? We are just removing 1 0 here, or anything that is there, right? And this division will be absolute divisions, right? This one, operand 1. So there will be a remainder, we will just exclude that remainder, okay? And we will just take this the quotient, okay? Now operand 1 divided by 2 to the power operand 2, okay? It's not divide, sorry, yeah, yes, it is divide, absolute divide, okay? So in shift right, what we will do is, um, let me write it here, we put, okay, so okay, when we do shift right, we will shift all these numbers towards right? So in that case, the leftmost bit will be like removed, right? It will be removed, but we will be having blank space in the in the left, right? So what we will do, we will do two things actually. There are two operations. There is arithmetic shift right, and there is Okay, let me write it here as well. So again, we will discuss all of these in great details when we will be discussing it. Okay, just a minute. Okay, when we will be discussing it in data format. Okay, format of data values. But for now, just get it this way, that shift right are of two types: arithmetic shift right and logical shift right. And in arithmetic shift right, okay, where should I write? Okay, let's delete little bit. uh, okay, let me write it here. In arithmetic shift right, in arithmetic shift right, the value will be considered as a signed value. Okay, which means the most significant bit will be the side, right? And when we are shifting towards right, then we will check whether this value is 0 or 1, and depending on the value that is present in most significant bit, we will what arithmetic shift right do is, it will put the vacant spaces, the put the this specific value in the vacant space. For example, if the value, like in operand 1 the value was 1, right? So the value that will be put here when we do shift right, uh, for just one bit shift right, in that case the this will be the vacant space, right? Now this vacant space will be filled by value 1. Okay, this one again comes here, right? Okay, so and so on. This is how it happens. Now when we do logical shift right, in that case it will by default consider the values to be unsigned. Okay, so the entire value is actually an absolute value, okay? And this will be positive. Therefore what it does is, it always it always fills the empty spaces by 0. Okay, empty spaces by 0. Okay, so we put zeros in leftmost blank spaces, the value of MSB in arithmetic SHR, and we put zeros in rightmost blank spaces. I'm sorry, let me say it again. So we put the MSB value in leftmost blank spaces in arithmetic SHR, and we put 0 in leftmost blank spaces when we are doing logical SHR. Okay, I think I'm making sense here. Okay, so this is arithmetic SHR, and this is logical SHR, and this is arithmetic SHR. Okay, again, if you are having little bit like doubt regarding SHR and SHL, then we will be discussing that, not an issue. Okay, so we will be seeing that there are many logics that are implemented inside ALU, because ALU supports various operations, right? So all the logic for all the operations are inbuilt within the ALU. Okay, and based on the operand, so this is actually operand 1, this is operand 2. These lines represent operand 1. Okay, these lines represent operand 1, these lines represent operand 2. Okay, and based on whatever operation, so this is actually, if you can see here, this is actually uh, uh, like operation code. Okay, so from here control unit will send, let's suppose, 000. Okay, now this 000, what it will do is, based on it is a decoder. Okay, now 000 will be decoded, and one of these logics will be uh, selected, one of these logics will get activated, and the logic that gets activated is will be based on whatever operation code we are sending here. 000 means we are activating addition here. Okay, and these opcodes, all the operand 1, operand 2 are going to all these logics, right? And since we are just activating addition, it will go to addition, and then we'll get the result. Okay, and this result will be stored in, this is accumulator. Okay, now this result will be stored in accumulator register here, and all the statuses will be saved here. So this is actually flag register. Okay, and this is accumulator. Okay, so this is how our ALU kind of looks like. This is nothing but a hardware implementation of all the logics that ALU can perform. Logics for all the operations that ALU can perform. Okay, so I hope I'm making sense here. So okay, so what we can do here is, so again we are seeing here addition as a black box, right? What is addition? Okay, let's take addition as an example. Let's discuss a little bit about addition. So we can see the hardware level or hardware aspect of ALU here, right? Let's see addition again. Like let's see addition, take addition and see how it is actually implemented. Okay, addition. We will take two examples, one from arithmetic unit, one from logic unit. Okay, let's take addition from arithmetic unit. Okay, and let's discuss what this black box actually means. Okay, so let's take two operands. Okay, operand 1 and operand 2. Let's operand 1 be 0 1 1 and operand 2 be 0 0 1. Okay, let's represent them by some nomenclature. Okay, let's name it A0, A1 and A2. Okay, and let's name it as B0, B1 and B2. So before implementing an addition logic, let's see how addition happens. Okay, logically. Let's write the logic. Let's see the logic first. Okay, so we have 0 1 1 and 0 0 1, right? So if you want to do the addition here, how do we do the addition, right? First we see these two bits, 1 plus 1, it is 2, right? 1 0, we take 0 here and we take carry 1. Okay, again 1 plus 1 2, we take 0 here, we take carry 1 here, right? Now this 1 plus 0 plus 0 carry plus uh, this bit from operand 1 and bit from operand 2, we add this and we get 1. Okay, so the value here is 1 0 0. Let's do the nomenclature for that as well. Okay, so let's suppose this is S0, S1, S2. Okay, let's take this as carry 0 and this is carry 1. Okay, and if we have any carry here, let's say it to be carry 2. Okay, we will follow this format. Okay, and let's suppose we have small units of half adders and full adders. Okay, half adders and full adders. What is half adder and full adder? So if we provide 2 bits, right, 2 bits here in half adder, it will give two things. It will give us the sum and carry. Okay, the sum bit and carry bit. Okay, so we were seeing here, right, 1 plus 1 is actually 2, right? When we give 1 plus 1 and 1 here, what half adder will do is it will take s is equal to 0, this one, and it will take carry is equal to 1. Okay, now this carry plus carry and sum duo will represent the number, the summation of these two bits. Okay, and what full adder does is it takes, instead of taking two inputs, it takes three inputs and it again gives carry and sum, right, in a similar fashion. Okay, for example, it is 1 1 1, so 1 plus 1 plus 1 is actually 3, right? So the biggest number that can be that can come out of this full adder is 3, right? Now carry will be 1 and sum will be 1. So this is half adder, this is full adder. Or let's suppose we have these. So it is very easy to implement this using the logic gates. You will see this in your digital logic classes. Okay, half adder and full adder are very easy to implement. Okay, let's suppose we have many half adders and full adders, and we want to implement the addition. Okay, this addition. So what we can do is, okay, let me take a pen, choose a pen. Okay, so what we can do is, we can take a0, this one, this is a0, right? And this is, so this entire thing is, let's suppose, operand 1, this is operand 2, and this is 0 0 index, this is 1 index, this is 2 index 2. So a0 and b0, let's pass these two via half adder. Okay, let's pass it via half adder. Okay. So what we will get? We will get s0, 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 right? Which is sum, and we will get one carry, right? Let's suppose this is carry, and let's name it as c0. Okay, we will get c0, this one, right? Now what we do in our second step, we sum carry along with the bits of two operands, right? Now we, at most, we will be doing the summation of 3 bits, right? So what we can do is, I'm so sorry. Okay, so what we can do is, we can put a full adder here. Okay, and this is c0. Okay, let me erase this. Okay, let me again write it. This is c0, and now this is a1 and this is b1. Okay, now again we will get one result, which will be the combo, carry sum combo, right? Now we will write sum here. Okay, this is s0, we will write sum here, so this will be s1, and again we will put carry, we will put carry here. Okay, let's suppose this is c1. Okay, now we will add c1 with what, a2 and b2, right, in a similar fashion. So we will again use one full adder, and we provide a2 and b2 here along with c1, and we get s2, sorry, s2, right? We will get s2, and we will get carry 2, right? So for example, if we have operand this and this, we can assume that our register has the width 3, right? Register has width 3. That means our accumulator will also be having width 3, right? Now this carry 2 is additional value, right? Because we will put s2 here, and we need to put c2 here, but we can't put c2 here, right? Therefore this c2 will go to carry flag. Okay. C2 here will go to, this C2 will go to what, carry flag. Okay, and this S0, S1 and S2, all these will be going to what, going to accumulator. They will be connected to accumulator, right? And this will be connected to carry flag. Now if we see this, so this entirely will be what, this entirely will be this, sorry, this part, this part, this part will be our addition black box, right? Why? Because now it is working the same in the same manner as we want. We are giving what, we are giving a0 a0 a1 b1 and a2 b2 as input, right? So we are giving operand 1 and operand 2 as input, and it does the operation, and it provides the result S0, S1, S2 in accumulator, right? And it provides this carry information in carry flag, right? So this is how an addition operation is kind of logically implemented using half adder and full adders, right? So let's suppose we have the we have the width of register X, okay. Therefore operand 1, operand 2 will be having X bits, right? So how many half adder and full adder are required? We require we require one half adder for one half adder for initial, because initially we don't have any carry, right? So just for initial step, first step, we will require a half adder, and then we will be requiring X minus 1 number of full adders, okay. One half adder and X minus 1 full adders in order to implement addition. So again, this is just to give you an idea like how these black boxes are also implemented. So everything here is a hardware component, right? So we can see here uh, everything here is kind of an implementation, and all these implementations are just kind of an intricate or complex structure network of logic gates, okay. These are nothing but this entire circuit is actually a complex or intricate network of logic gates, okay. So the ALU is not different, it will be the same. So I hope addition is clear. So let's take one example from logic unit as well, right? So what should we take? Let's take numerical check whether a number is zero, okay. Let's take this one only, okay. Let's check how this zero flag is getting populated, okay. Let me add one slide here, just a minute. Okay, so let's start a discussion. Let's do numerical check. Numerical check. And numerical check is if zero, okay. Okay, so let me build a circuit that tests if the output of this ALU is zero, okay. So let's take accumulator, okay. Let's consider the value inside accumulator be an 8-bit value, okay. So it can be A7, A6, all these are bits actually, okay? A4, A3, A2, A1, A0. So these are 8 bits that are inside a accumulator, okay. Now in order to so in order for this value to be 0, all these bits should be 0, right? A0 should be 0, 1, 2, 3, 4, so on up to A7. Sorry, the value should be, all the bits should be 0, okay. So let's see how we can do that, how we can check if all the values are 0. So let me build a circuit here, okay. Let me take uh, the combos here. Let's take A0, A1, let's take A2, A3, A4, A5, A6, A7, okay, these combos, and let's pass it through OR gate, okay. So if we pass it through OR gate, we will be getting 4 values, right? 4 bits, okay, as a result, okay. Which will tell, so if either of this, so if all of them are 0, all like A7 and A6 should be 0, right? So the result here should be 0. Similarly, result here should be 0, here should be 0, and here should be 0, right? Even if just one of these values are, one of these bits are 1, all these fours cannot be 0, right? One of them will be 1, or more than one of will be 1, right? So these 4 are now 0. Now what we can do is we can again take the combo here, like pairs here, okay. and again pass it through OR gate. Okay. Now, if any one of them, if any one of them is 1 here, that means any one of so at least one of these will be 1 here, right? In that case, the result here won't be 0 0, right? The only possible way that the result here will be 0 0 will be when all these bits are 0. Similarly, if we pass again these two bits, the results, through an OR gate, in that case we will get just one value, which will be either 0 or 1, right? So this will be either 0 or 1. So it will be 1. This value will be 1 when any one of these bits are is 1. Okay, any one of these bits is 1. That means when accumulator is not equal to 0, right? When value inside accumulator is not equal to 0, and it will be 0 only and only when the value inside accumulator is 0, right? All the bits here are 0, right? So we can say that this entire part is numerical check for if 0, right? This is a numerical check for if 0, and the result of this numerical check will be going where? It will be going in a flag register. Where exactly? In 0 flag, right? In 0 flag, right? So again, you can see here it is nothing but the combinations of different logic gates, right? So if you see a numerical check here, if you see numerical check here, we don't have any numerical check in this example, but if we have some numerical check here, this numerical check will check whether the accumulator is 0 or not, and based on that it will fill this flag register, this 0 flag or flag register accordingly. So we have taken one example from arithmetic unit, one from logic units, and we have a rough idea of how our arithmetic and logic unit or ALU looks like. So it will be combination of arithmetic unit and logic unit, and all the operations will be implemented here, and sorry, and any one of these operations will be selected by control unit, and it will perform this operation and the result will be saved in accumulator. Okay, so I think we don't need uh, uh, to go more into details of ALU, because as per the gate is concerned, uh, gate uh, I mean gate does not ask more in depth from ALU. Okay, so it will just take ALU sorry, it will take ALU as a black box, and all these discussions that we did here are actually just to give you an idea how our ALU looks at hardware level. Okay, so we have covered registers, we have covered ALU, and we also know that data path has this CPU interconnections. So we will have one example where we will be implementing this entire data path. Okay, and we will check how different operations are performed. Okay, now since data path is used to perform operations, we will exactly discuss what an operation is. Okay. So in our next class we will discuss, okay, let me add one more slide here. So in our next class we will discuss micro operations. Micro operations are nothing but, so say when we are implementing instructions, right? Sorry, when we are executing instructions, execution of instruction means execution of sequence of operations, right? So these sequence of operations were actually micro operations. So we will be discussing what micro operations are, and then we will see one example of data path. Okay, we will see one small basic data path, and then we see then we will then we will try to dry run few micro operations on these example. Okay. So that's all for today's lecture. Thank you.